I don't remember. Where we can't have class, we don't completely understand. We just postpone everything a week.
No, we turn it. The rule is that we turn it online, fully virtually online. But I'm 100% sure I have allergy, because again, Every time I start to sneeze, all I take is just, I open the news, the wizard.com, and it's always reg week, very high today. And that's why. And also because you will see that it's like I will sneeze every 20 minutes, kind of. Like I will sneeze for like every 20 minutes and then perfectly fine. And then 20 minutes again, exactly, and start sneezing again. So it's very, very well timed. All right. So we're gonna start. And people online, can you please confirm that you can hear me?
Yes, we can hear you.
Thank you. All right. So we will go through the homework solution and we will go through the project, which is due next week too, right? And so hopefully we'll have a lot of time for that. Okay, and actually, let's make sure that, you know, 7 o'clock, if I don't stop talking, you stop me and tell me now solve the project for us because it's due in 1 week. So we'll have enough time for the project. But I want to start with the class notes. I mean, let's continue our journey in chapter 12. So chapter 12, we are dealing with mixtures, specifically air and water vapor mixture, right? And we said this is very relevant to HVAC application because they care a lot about humid air. As a matter of fact, we said that it's this latent load, we call it latent load, the amount of water vapor that we need to get rid of. That's actually a lot of what HVAC is about. It's about getting rid of that water vapor. So if it wasn't for that part, you know, our electric bill would have been way cheaper, right? So that's why it's this, that's the big application of those water vapor mixture. And yes, last time we basically talked about how we can characterize the air by two things, phi and omega, which what I usually make a mistake and call W, because I guess when I was undergrad, I learned as W and got stuck in my mind. So what is phi? It's the ratio between the pressure of the water vapor in the air. We call that the partial pressure of the water vapor. Because this 1 atmosphere room we are in, water vapor only part of this 1 atmosphere, very small part. That's the partial pressure. So that's P vapor. And so at this room, let's assume this room at 25 degrees C. This room at 25 degrees C, that 25 degrees C, if you open the TS diagram of the steam of water, that's TS diagram of water. And you find out with a 25 degree, what is my B saturation? That B saturation will be the highest pressure that the water vapor in this room can go to. Because if it's higher, if the water vapor in this room have pressure higher than this, and it's still at 25 degree, because the room is 25 degree, that high pressure will end up being where? It will end up being like this, then like this, then like this. Okay? So he will intersect with the 25 degree in the compressed liquid region. So that's why at 25 degrees C, whatever the room temperature is, you can be here, that is saturated, or you can be here or here or here or here, right? But the maximum you can be here. You cannot step to the other side. Otherwise, you compress. So now how far your pressure is compared to this P saturation, that is your phi, the relative humidity. Yes. This guy, Yes, yes, yes. This guy, right? And also maybe we can make this. I think that's the best we can. Okay. So when someone say 20 degrees C and 40% humidity, then he mean that you can get your P vapor from knowing B saturation multiplied by 0.4, then you'll be able to get this. The second important ratio was omega humidity ratio. So phi relative humidity and omega humidity ratio. And it's how many kilogram of water per kilogram of dry air that you carry. And through this equation, we figure there is a relation between omega and BV. If you know the vapor pressure, you know omega. If you know omega, you know vapor pressure. Okay? And you can see how we talk about that derivation now. And we talked about the enthalpy of the mixture, which is enthalpy of the air plus the enthalpy of the water vapor. Both of them get multiplied by kilojoule per kilogram. Okay. So one important thing about this is that the H vapor, where do we get that? If you want to get the H vapor, you want the enthalpy of the vapor. Where do you get that? Where do you go to get the enthalpy of the vapor? Steam table. And HA, air at 25 degrees C, and you want to get is enthalpy. Where do you get that? Huh? You get from X team? No, H air, you cannot get it from X team. X team is for vapor, water vapor. HA, where do you get that? Table in the back of the book that say air properties, right? There's air table, just like steam table, there's air table. And before this course, probably you have used also CBT. Like if you won't get the enthalpy of the air, you just say it's CBT. Constant CP. 10, like usually in they will tell you the CB, assume the CB of the air is 1004 or 1004.5 or 1005 joule per kilogram. Right? Joule per kilogram Kelvin. That's the CP. So the enthalpy is joule per kilogram, but the CB is joule per kilogram Kelvin. And that's why the enthalpy becomes CBT. Right? You multiply by T to knock out the Kelvin. So it becomes joule per kilogram. So why I'm saying this? They come from two different tables. Funny enough, those two tables don't have the same 0 point. Like the H at 0 degrees C is not, you expect all of them to have like 0 temperature or something. No, they have different different starting points. And so it's not really a problem because most of the time what we care about is not the absolute value of H, but it's the difference in H's. So what I'm saying is that although sometimes you could have the table at different table sitting at different references, it doesn't really change the solution because all the time you always ask for delta H. And for example, if you ever manage to download and install Cool Prop, and one of you actually sent me an email over the weekend, like I would like to install this Cool Prop before the project because the project have 3 refrigerant. I don't want to go and keep checking my steam, my thermodynamic book to get the reference. Wouldn't it be nice to just have something like X steam, but for refrigerant? And then I would tell him, you know, R154, give me the enthalpy. Ammonia, give me the enthalpy. And I didn't reply because I don't really know how to install it. I actually install it on my smaller Mac by luck. And then when I tried this semester to install it in my big Mac, it's giving me hell basically because it's not really running under MATLAB, it's running under Python. And then you have to tell MATLAB to use it from Python. And then if MATLAB has the wrong version of Python, then he will not be able to pick that one. So it's a little bit of software installation problem. But I mean, we are not desperate for that cool prop. But if you can, that would be nice. Anyway, why I'm telling you that story? Because you can see here in cool prop, he will tell you that you can set the reference according to different standards. So for example, ASHRAE, what's ASHRAE? American Society for Heating, Refrigeration, and Air Conditioning. Okay. So the society of, they have the table such that the enthalpy and entropy are set to 0 at minus 40 degrees C. Your thermo book could be at 0 enthalpy at 0 degrees C. So then when you use the thermodynamic book with the steam table or thermodynamic book with the psychrometric chart, you may find different value for H's. Okay, but at the end of the day, it doesn't really matter because it's the difference, and difference is always correct. It's just like where they're gonna put the 0. That's the only problem, right? So they tell you, see here is, so those people put it 0 at 1 bar, those 0 put it at minus 40, those people put it at 0 degrees C, right? Saturated liquid, those are all where they start counting. But again, the difference is always the same for all those things. Make sense? All right. So the H of the whole mixture, air and vapor, right, is like this. And if you take it per unit mass of air, then it becomes this. It's H air plus omega HV. So this is per unit mass of dry air. You multiply by m dot dry air and you get the total H. Okay. So you will see in the example today, whenever they always calculating the enthalpy, they are doing it like this. It's H plus omega HV. It's basically trying to acknowledge that I don't have the same mass flow rate for both of them. The air is coming as m dot air, the water is coming as m dot water. And so if I want to get the total enthalpy, I better multiply m dot air by H air plus m dot water by H water. And so if I want to make it per unit mass, now the problem is which unit mass? Air, water, or mixture? And you would think that the thing that makes sense should be the mixture, but no, the convenient way, even if it does not make sense, is to use it per dry air. And that's what the psychrometric chart was basically normalized with. So the enthalpy kilojoule per kilogram dry air. So I think I posted 2 psychrometric charts for you, one in English unit, right, and one in SI, right? Is that the case? Can anyone click on the psychrometric chart and make sure we have 2 pages there? We have 2 pages, right? Good. So because you're gonna use the SI one in the quiz today, so it's good that you have access to that. The SI. And although the conversion is not a problem, right? We know how to convert from degree Fahrenheit to degree C. Minus 32 multiplied by 5/9. But still, it's convenient to do this. Okay, so this chart, we talked about this chart and how useful it is. The dry bulk temperature on the x-axis, omega on the y-axis. All those curves are for different phi, and the vertical lines ending with that scale are the H, right? Those not that steep curves are, anyone? What are those 0.9, 0.9, 0.88? Specific volume. Okay. So cubic meter per kilogram. It's the opposite of the density. It's not kilogram per meter cube. It's meter cube per kilogram. So you need this. We said why? Because you want to convert E dot to M dot. The problem would come with a cubic feet per minute, and you need M dot for the enthalpy. Multiply M dot by the H. So that's why those guys. So that was the psychrometric chart. And in the book he had, or in the last time we went through a bunch of stuff that he basically showing us how we can use a psychometric chart, how we read the omega, how we can read the dry bulb temperature. Sorry, what is that? That's the dew point, right? Dew point temperature, remember? Dew point temperature, we go like this and we read down. And of course, phi and the insult, total insult. Okay. Very good. So what we're going to use those charts and those equations for? Those three applications. Dehumidification, which is reducing the humidity, humidification, which increase the humidity, and mixing of two airstream, and that usually happen because why? Because of that AHU, the air handling unit. You bring the return air, you mix it with the fresh air, and you come up with a new stream. That's the one that go to the house back again. So you need to be able to find out what is the property of that mixture. Okay, and that's basically what this part is about. When you have this and this, 40%, 30 degree, 10%, 15 degree, you know, coming together, what will come at the end? All right, so the dehumidification is where you have air coming with W1 and you wish, and phi1, and you wish that when he come out here, you will have less weight, less water. Okay. So how do you do this? By cooling it, right? This is a cooling coil. What's a cooling coil? Very cold refrigerant. This cooling coil will be we can. So that cooling coil will be part of a refrigeration cycle like this, right? Where this is a compressor, condenser, expansion chamber, and the evaporator. That evaporator is our cooling coil. That's the guy that's pulling Q dot L, right? So this guy is the one sitting in here, right? This is the cooling coil, the evaporator. So the air come at T1 and then he leave way colder. And when he leave way colder like this, his W2 become less than W1, right? Because in the psychometric chart, what will happen? I have my psychometric chart. Yes, here. So let's say that I am here at T1, 35 degree, and let's even go up a little bit. So, but maybe here, what is that? 60%? No, that's 50. 60% would be here. So 35 degree and 60%. Okay. So if that cooling coil take me down to not just 30 or 25. So here's 30. If I cool at 30, I'll become like this. Same W. 25, I will come here, right? Slightly smaller W. But if that cooling coil can take me to 20, compared to where I was at 35, that difference between 35 and 20, when you read the W omega over here, it's 0.022. And if I go to 20, I will go to 0.015. So 0.022, you see where I'm reading? 0.022, and at 20, I'll be like this, 0.015. That is what? That's kilogram water per kilogram dry air. So multiply this by m dot air, and that will be how much water is dripping in the collecting tray over here. You just open the valve and that water will flow. Okay? So this is the mechanism by which they can reduce the water. Notice how phi2 is 100%. Why is that? Why phi2 is 100%? Because when you are here and you are cooling, you cool like this. And once you stop here, once you got this temperature, that is your, what would you call that temperature? That would be nice, but no. What do you call it? Dew point. That's the dew point for that air. The air at 35 and 60% relative humidity, that is his dew point. If you go less than the dew point, then the air would come down like this all the way. Okay? So when you leave here, you leave 100%. You are on that curve. Okay? Remember that. There is a free quiz coming at the end of the class related to this. All right? So the water now that's falling is probably going to be very good assumption for it. It's that it's have the same temperature as the air leaving, right? Is there any chance it will have anything else? The water coming down, this T3, is there any chance she will have different temperature than T2? Free quiz if you tell me yes, but you explain why. Yes, it can have a different temperature, explain to me why. Also for online people, you can answer and get free quiz, so you don't have to solve the quiz today. Repeat the question. The question is, in this dehumidification process, where the air lose his omega drop, because we are using cooling coil, that water, the difference between W1 and W2 will fall down as m dot water. And he said there that T3, the water temperature, is equal to T2. So the question is there any other outcome rather than T3 equal T2? Could T3 be different than T2? And if this is the case, which is the case, why? Why T3 really can be different?
Because it loses heat when it condensates.
Well, yeah, it loses heat, but I mean, it doesn't condense at the same temperature like the air from this chart. I mean, we are at 35 and 60, and then we get cool like this, and then because the air is leaving at 20, the water also is condensing at 20. Why would the water have different temperature than the exit air? Ariane said yes, because it's different pressure. No, they are sitting at the same pressure. The liquid water, I'm not talking about the partial water in the vapor, in the air. The partial vapor, the water vapor in the air is having different pressure than the air. Both of them share the atmosphere. But the water that's falling down on the floor, that one is sitting at the atmosphere. No, it's not. Anyone? Okay, the answer is, I'm gonna get my free quiz. The answer is, how are we cooling that thing? We send it into an evaporating coil. How does this evaporating coil look like? Bunch of pipes with bunch of fans, and the refrigerant come here at 3 and you leave at 4. And here is so air at T1 and air at T2. And we said in that, you know, example, we say 35 and we're gonna cool at 20. How am I gonna cool the air at 20 again? I need refrigerant to do this for me. And what's the temperature of the refrigerant? Huh? Yes, it has to be below 20 so that I can cool air to 20. That refrigerant is probably coming here at, I don't know, like maybe 5, and he's leaving at 15, right? And the water condensing on the coil, they are hugging the coil, right? And they really have quality time together. What will happen to that water sitting on the coil? It may subcool. So not only it will separate from the air, but it will also, the air that's 20 and it's leaving him at 20, but it will get subcooled, right? So the, huh? Yes, of course, because I mean, you cannot be cooler than the something that is cooling you, right? But my point is, it's different. The exit temperature of the air and the exit temperature of the water could be different because the water is in close proximity to the coil. They condense on the coil while the air is moving through the coil, right? So there's a chance of a little bit subcool. But having said that, this is a very good approximation and without knowledge of the heat transfer. See that part of like how much does the water get cooled to? That's heat transfer, not thermal. We're gonna go through heat transfer after we finish the thermal part of the course, right? So it has to do with the heat transfer rate and the geometry of the heat exchange. Okay, very good. So what we basically people need from this is to figure out, you know, that ratio m dot water over m dot air and the q dot over m dot air. How much cooling you need and how much water you'll be able to subtract. Okay, so now let's jump quickly to our project 2 and figure out the similarity between this and this. So what is going on here? This is the refrigeration cycle, right? Where this is the evaporator and this is the condenser. This is the cooling part and this is the heating part, right? And so R1, R2, R3, R4, what is that? That's the refrigeration cycle. I can just plot this in a pH diagram, right? So it go in the compressor at 1, get compressed to 2, then cool to 3, then expansion take you to 4. Make sense? Refrigeration cycle. So why does he need to cool? What is he cooling? He's cooling water. He's cooling very cold water. Okay, why? Because that water over here go to this chamber, it's called the condensation chamber, where hot, humid air is coming. And this hot, humid air, when he see that cooling coil, what happened to him? That happened to him. He come humid and hot, and he leave cold and saturated. And he drop his water. Make sense? Right? So this is exactly This is exactly what's happening over here. Hot, humid air and a cooling coil, right? And it basically leave and drop his water. Now, how did this air get so humid and hot so that we can cool him and drop his water? Let's look at the air cycle. You see the air cycle? What's going on here? Air, A1, get into a blower circulate basically. What's the difference between blower and compressor, by the way? Are they the same thing or different? Very good, yeah. So blower is really a compressor with very small pressure ratio. I mean, when you look at the blower, he's basically just like a magnificent ceiling fan. You know, a ceiling fan that is like one hell of a flow rate. Just, but I mean, you just like put in a big duct and it will never be able to seal that well. It will never be able to push because it has a lot of tolerance in it. Okay? So a blower is just really a very big bad compressor. Bad because he cannot compress that well, but he's really big, so he sends a lot of fluid through it. So there's not that much pressure drop in this cycle. That's why he's happy with a blower, not a compressor. Okay, so you just send the air through, and what happened here? You throw it through a bunch of sprays. We will discuss them in a minute. We're going to go through humidification. But basically, you can tell that if this water come here, and there is a lot of this backing material, it's like similar to cooling tower. They wanted the air and the water to hang around for a really long time. So that's why they let it drip into a bunch of trays, kind of trickling trays, so that the film, water film form and drop, and meanwhile the air has to navigate all those passages. So as a result, basically, when the air leave here, ideally speaking, he can be 100% humid because you just send him through tons and tons of water passages. You had very big chance to hang with water for a really long time. It's the inside of, you know, those humidifier that we put them in the winter, where like you have this fibrous material and it absorbs water and you let the air go through. That is this part. So the air come here, humid for sure, hot because the condenser of the mechanical vapor compression cycle that was cooling here, that condenser have this Q dot L plus work compressor as Q dot condenser. And guess who get this Q dot condenser? That water. So the water come here very hot, get sprayed, get spread all over the place, and the air basically hug all that water and leave 100% humid, ideally speaking, and hot. So when he leave like this and hot and humid, he come here, he drop the water because he gets so cold again. So this one humidify him, this one humidify him. Okay, and what is this water? This water is sea water, the salty water, water with salt content in it. So when the water evaporates here in the air, what evaporates? The salt will evaporate. Only pure water evaporates. So pure water evaporate and the air carry it, and then the air drop it in this place. So the prime or the seawater gets sprayed and very concentrated brine come, but the clean water separated over here. So W5 and W4 equal to W1. The flow rate of the water, W1 first it get cooled. Seawater get cooled. This is the minimum temperature in the cycle of the water. Water cannot get any colder than this. Why do you want it that cold? Because you want to let the air drop on it, right? Then it gets hotter to W2, then it gets super hot at W3. That's the maximum temperature. And then when you spray it in the air, it heats the air, but what happened to the water itself? The water will cool down. right? And it leave at W4. Leave at W4 concentrated, prime, because you took some of the water out. So if you started with 35 ppm, 35,000 ppm, for example, here, you leave like, I don't know, 65. I mean, maybe depending on how much water you are sucking out of it. If you suck all the water, because you do such an amazing job spraying and humidifying, you could end up just like with salt crystal drop. They call this ZLD, zero liquid discharge. No water is left alive. All the water has been sucked into the air. Okay. So this is not just for seawater desalination. This is also if you wanna treat produced water. This is exactly one of the techniques that one of the companies in Oklahoma operate their produced water treatment facility. So what is produced water? For every 1 barrel of oil that we get from Oklahoma, we get 10 barrels of water, bad water, water that was hanging with oil, chemicals, tons of chemicals in it too. Especially if you are using fracking, hydraulic fracturing. You have all those bacteria, inhibitors, and lubricant and bad stuff. So that water, a lot of water, you cannot just be injected again into the ground. They do that right now, right? They inject them in, they call them class 2 disposable well. So those are empty well. They don't have any oil anymore. So we can put the water back into the ground. But if you put too much water, that's when you have earthquake, right? That's why Oklahoma is the second after California in earthquakes. Okay, unfortunately, ours are so small, you don't notice them until they go to 4 or something. But they are because we are putting all that oil. So all that water back in. So this company basically, what they do is that they tell you, well, give us 5 trucks of water and we will turn them into 1. Okay. And how do they do this? By humidification, dehumidification thing. They basically take air, and not exactly the same cycle, but one chamber that they basically take the water into the air, and then they drop it on the other side by condensation. And when it condenses, then that heat basically go to do the other side. Okay. And so they tell you, they say we make it by rain, or we make it similar to the raining process. We let the water in. And so you get really clean water that you can drink. But what's really important is the amount of brine that you collect is only 1/5 of the original water. So rather than having 5 trucks that you get rid of, you only get 1 truck. Concentrated brine. And then it's cheaper to just ship 1 truck back, also cheaper to inject 1 truck rather than 5 trucks. Okay. So does this process make sense? So you got the refrigerant, right? And you got the air, and you got the water. Okay. And this guy and this guy, you're gonna see the example solving them exactly so that you see how much water is actually coming down. Question so far? Do we use the heat pump equation in the project? I mean, that is really the difference between the 3 refrigerants. So in the project, when we say, well, now figure out, you know, which one of those guys will work. You are really comparing 3 refrigerants as candidates for this cycle. We have to, because how you can evaluate their performance? It's by the COP. I'm going to calculate the COP. Okay, I got your question now. What's your name? Jared is basically saying, are you going to use the Q dot L over WC or the Q dot H over WC? Because the problem here is we like this guy. This guy is important, but we also like this guy. You see the problem? Like most of them are important. So like how could you tell that this refrigerant is better than this one if this guy is doing well in Q dot L, but the other guy is doing better at Q dot H? Right? That is a question. Yeah, I'm not gonna answer that. I want you to figure out how we're gonna judge the refrigerant in this. But at least we know exactly what this cycle is doing, right? It's taking heat from here, sending it over here, right? And at the end of the day, what do you really care about? At the end of the day, in the cycle, what do you really care about? How much water, m dot water per m dot air, basically, right? That's what you really care about, m dot water over m dot. From the continuity equation, yes, the water coming here will split into two ways, 4 and 5. But notice that this W1, as we're going to see today in the homework problem number 1, that flow rate is not just pure water. It's m dot water plus m dot salt, and the m dot salt will leave intact, right? It's the m dot water that gets reduced or split. So incoming here is not just m dot water; it's m dot water plus m dot salt. We will see it in the okay. So let's see in that cooling coil, how we get this m dot water and how we get the Q dot. So how does he get the m dot water? That's simple. That's W2 minus W1 minus W2, because W1 is the bigger. W1 minus W2, right? Multiply by m dot air. So it's important, just like in that seawater, where you have two species coming in, salt and water, you do kind of like two mass balance. Here, there's water vapor, and there's air. So the air come and go intact. It's the m dot water that basically gets split. Some of it will leave with the air, but the rest just drop. That's why. So same thing when you think about the salt. The salt would be coming and leaving as it is. It's the water vapor that will get split. All right. So of course at the exit, because saturated, getting W2 is easy from the chart. And at the beginning, you just need T1 and Phi1 to get W12, right? And so once you have those two W's, you can get m dot water, m dot. Make sense? So here, when I look at this project, right, this flow rate is simply this W minus this W. W before the cooling coil, W after the cooling coil, multiplied by the m dot. Yes? It's exactly the same like this example. That's exactly the same equation you're going to use. Now for the energy to get the cooling coil, where do we go to get energy stuff? First law of thermodynamics. You put a control volume into this, and you will see one inlet and two exits, right? And the Q. So this equation, that he writes it like this, this is simply, he's writing it as things coming in and things that are leaving. Okay, so I, on the other hand, always like to respect the sign convention of the first law of thermodynamics. Okay, and so when I When I do this and I write here 1, and this is 2, T2 and W2, and T1 and W1, and this is m dot water and H water. And then actually the Q, because it's leaving, is going to be like this, Q dot coil or Q dot cooling or something. I mean, we can just call it Q dot C. Okay. So when I'm writing the first law of thermodynamics and I'm going to say Q dot minus W dot, we cancel this because there's no word, equal to M dot H2 minus H1, where this H, I mean H total, which would be air plus water, right? So the Q dot coil and Q dot coil, because it's leaving, that is negative. So I'm going to say minus Q dot coil because it's leaving, equal to M dot, and this H2 minus H1 would be H2 plus omega, right? Omega 2, right? H vapor 2 plus, and then minus, this is M dot air, H1 plus omega 1, H water 1, or H vapor 1. And then let's not forget that this guy is also leaving, right? Plus, so since it's leaving, so plus M dot water, H water. So when I do this, then my Q coil will end up being positive. The actual value would be positive. This will end up being 7 or 8 or 10 kilowatt because I already put the direction in the equation. Okay, so I just always think, you know, when we always say sigma out minus sigma in the first law, things will work much better than just have to worry about who's input and who's output. So what I'm trying to say is that if you just have a rule and you apply it blindly, but you apply it in the right way, things will come out correctly. So I don't have to worry about whether this is done by the pump, done on the turbine. You know how we can get confused on the sign of the pump work and the turbine work. The same thing for the Q. So when you just tell yourself, I'm just going to always write Q dot minus W dot equal M dot out minus N, then you may not, you will not really go in your own. Okay. So eventually this will turn exactly like this. Okay, we look at this. It's Q, and it's going to be plus now. And he's saying out, or here is the two guys out minus N. Okay. Does this make sense? Very good. So obviously this W minus W is M dot water. And so to get how much cooling is needed, you just need to get the H total at 2 minus the H total at 1 plus M dot water H water. Since we are assuming the water is leaving at T2, then we can open the steam table and get H water at T2. Right? And those two H's, again, they're per unit dry air. So we can just read them from the chart directly. Make sense? Questions? Very good. Needless to say, that H water, even if you do it, if you get it from a wrong steam table, not wrong steam table, a steam table that's not normalized the same way like the cyclomatic chart, it's multiplied by a very small W. So that part is not going to change the results that much anyway. Okay, the cooling that you are paying is really for the air. And the amount of the water that's falling, it's not gonna It's the difference in the H is not going to be that much. So he's saying you get this H water from HF, from steam table, HF. Remember HF is the liquid, HG for the vapor, right? Very good. So use 1, 2, and W1 and W2. All right. So now the opposite of the dehumidification is the humidification. If you want to increase the amount of water vapor in the air, and that's basically happening over here. Okay, in this guy. So how do we calculate the new temperature? Air is coming, and you'd like to figure out what is the air leaving. Okay, so how are we going to calculate how much water and how much temperature does he leave at? To start with, do you think that air at T1, let's make it 20 degrees C. You think when you leave, you will leave at higher or lower than 20 degrees? What do you think? Does the air when it gets sprayed into a humidifier, does it get hotter or colder? Huh? I heard colder and I heard hotter. And you are right to be confused because it can do, that's a trick question. It can actually do both of them. It can get colder or hotter. There is something called evaporative cooling. And as you can guess, evaporative cooling is all about getting T2 lower than T1 by spraying water into it, right? So how is that possible? If you are here at T1 and you have W1, if you spray the right amount of water, you can go to, yes, higher W2. As a matter of fact, you can go to P2 equal 100%. But guess what? You can actually go to a lower T2. And you are moving here along constant H. This is basically you are saying that I am bringing water at T1. The water and air are the same, but when I spray the water into the air and the water evaporate, but the whole system is adiabatic, no one is cooling, there is no refrigeration, I'm just spraying water in air. Then along that line, what happened? Constant H, the budget is the same, but you are splitting the budget between air and water that would like to evaporate, water that would like to turn from liquid to vapor. So where the water is going to get its latent heat? From the air, right? And so although the total H is constant along that line, but you are cooling the air, right? And so you can do this especially in desert condition or arid condition when phi is less than 100%. It's way, then hopefully if it's dry heat, then the humidity will be less than 100%. And the lesser it is, the better, because you can start, imagine if, yes, T1 is hot, but W1 is really small. So rather than here, and you reach there, no, you start at even lower W. What happens if you start at lower W or omega? You go to a lower temperature. T2 can be even colder because you start way low. The lower the omega that you start with, the more enthalpy that you're going to suck from the air to evaporate. Because you have huge room to add more and more water vapor into the air. So rather than finishing here, we could finish here. Right? So that lower, or this idea, is actually let's do it here. This idea can think of it as don't have a good sketch to show you, but basically if you send the water into an underground or a cold water basin or something, then the air get cool because he need to evaporate all that water, and he will come to you really cold and yes, a little bit humid, but if he is already very dry to start with, you don't mind, huh? So if it's like he's like 10% or something relative humidity, and you push him all the way to 30% or 40%, that's okay, right? So something like this, there will come sea water, and then by the time he leave over here, he's actually colder. Yes, a little bit humid, but still colder. And he did it for just by evaporating a little bit of underground water. And then you see this part too. This is where the sun is heating the chimney. Okay, so that's like passive cooling. Underground for passive cooling. Okay, so the air is getting all the moisture from the ground, and it's helping him to cool, right? And the sun is driving the flow up by points. So the whole place is being cooled without any mechanical work. Does this sound like a good project for number 3? Maybe we can think about something like this, how we can design something like this. Figure out what is the maximum temperature drop, for example, and figure out things like how much the height of the chimney to be able to do this, right? So let's take this, put it here. We'll think about it. All right. So that's what happened in evaporative cooling. When the water have no source of energy but the air that is trying to carry it around. And so he will drop, the air will drop. But what if the water is really hot, hotter than the air? I mean, of course, the air will not get cooler. You probably may be hotter. And just to be on the safe side, let's not even inject hot water, because you may think, well, hot water, but I still need my HFG, right? I mean, even if the HF is high because the water is like I'm spraying water at 80 degrees, but it's still water. And to get the HFG, which is a big deal, the air will have to pay, the air will get dropped. But what if we actually inject steam? Then it's a done deal. You inject steam, of course, the temperature will increase, right? Because I mean, it's ready to go. So note that in this project, I mean, he's trying his best to put really hot water, but also the spraying part, when you spray the flow into a mist, into a really tiny droplets, the evaporation happens so quickly. I mean, you still need to pay the HFG, but the rate happens quickly, right? But just atomizing doesn't mean that you are vapor, just that you have very tiny liquid problem that still need their latent heat. Okay. So in the humidification, when he's injecting, here is the air and here is water as vapor. So that would be already ready to go. So it will just add insult to the air and will take him up, or liquid. Okay. And then you will leave moist, of course, and that's the part. If T2 is less than T1, you did cool, and if T2 is bigger than T1, you go this way, that you didn't heat. And so in both scenarios, look at W1 and W2. In both scenarios, you go up in the cyclometric chart. What that means? You increase the humidity of the air. There's by how much? By the m dot water you're throwing in. Okay. But now whether you're gonna go to the right and you are heating, or you're gonna go to the left and you are cooling the air, that will depend on the H3. Okay. So H3, the energy, applying the first law of thermodynamics over here, where we're gonna say no external heating, no external cooling. Therefore, m dot delta m dot H plus m dot H equal m dot H. That H3 will tell you whether you're gonna go higher or lower on the exit side. All right. Let's check. So the question say, does the water vapor being injected need to be at a certain temperature? Well, you need to, depending on what's the outcome you want, right? So the equation that we will drive right now, that equation will tell us what is the relation between the exit T3 and the H3. There is a relation between the two of them. You know the one, then you control the other, or you figure the other one. So if you say, I want my air to get that hot, or that temperature, that will tell you what kind of H you need to inject. I mean, obviously the m dot 3. So what we have in our hand, if we are designing something like this, is two things that we have in our hand. M dot and H. How much flow rate we should inject, that's our pump, and how much heating should we add to that water. That's our heater sitting on that water. So those two things are related to the outcome. M dot 3 will control, help, M dot 3 will control playing with M dot 3, what will it change? Come on, guys. Control what? Yes, omega 2. M dot 3 will control omega 2, right? Because omega 2 minus omega 1 multiplied by m dot air is m dot water, right? That's the first equation. That's the continuity equation. Remember, we have only three equations: continuity, momentum, and energy equation. So the continuity equation will tell you m dot air multiplied by W2 minus W1 equal m dot 3, right? Or m dot water. So those two guys that we are, this is our target, and we will reach them by controlling those two knobs that we have in our hand. Okay, so you write the continuity for the air in equal air out, yes, and water. So m dot vapor plus m dot 3 equal m dot vapor, and when you divide there, when you actually realize that m dot vapor is W m dot air and W m dot air, and then you divide over m dot air, this equation, this continuity equation, become W2 equal W1 plus this, or simply W2 minus W1 is m dot 3 over m dot air. Okay, so that's the first equation. Now for the energy equation, right? Again, I will actually, I don't like it this way. I would start from here. No, where I would start? I would start from here. I would write my equation like this. I would say Q minus W. Q minus W equal, and of course, Q is 0 and W minus equal 0. And then I would say what is out minus what's in. So I will flip this out. But anyway, so he's basically saying that guys that's coming equal to the guys that are leaving. All right? And what's coming? M dot 3H3 and M dot air, H air, and M dot vapor, H vapor, or what I would call here simply M dot air multiplied by H total 1. And what's leaving? M dot air times H total 2. H total, the whole mixture per kilogram dry air. Okay? All right, so just rearranging this so that we can put our hand on H3. You'll get it like this. And it's very clear that T2, which is controlling this, both term, T2 is controlled by H3. For the same M dot 3, if you are done with M dot 3, just playing with H3, hot or cold, will take a T2 with it, up and down. Right? And this is nothing but simply first law, M dot H plus M dot H equal M dot H. I mean, the only thing that he did here is that thinking that M dot vapor is simply W or omega times M dot air. And then dividing the whole equation by M dot air. That's what he did. There is no magic here. Right? So this equation simply tell you that if you start from 1, 2, the way that 2 will be controlled, the only way that 3 will be controlled, sorry, the only way that T2 will be controlled is by H3. Okay? So I wanna tell you, graphically, the equation may be a little bit complicated, but graphically it's a piece of cake. So this is our cyclic chart, right? And we know T1 and omega 1. Okay, I want to find out what happened for me after I spray that spray. Okay, which is coming at T3 and M dot steam or M dot, let's call it M dot 3, whether it's steam or vapor or water, liquid. So I want to get my 2. How get my 2? Omega 2 is omega 1 plus M dot 3 divided by M dot 1 or M dot air, because air 1 and 2 is the same, right? So if you have this knob in your hand, you can see where is omega 2. Okay, so it turned out, like omega 1, let's say it's 0.01 or something, and that extra thing will tell you are at 0.02. So you draw a line here, and that line is where you expect W2 to. Okay? Now for the enthalpy, you already are you know where you are, T1 and omega 1. You can just read. What do I read if I go up like this? What do I read when I go up on a scale here like this? H, right? H total. I mean, let me just call it H capital. I mean, it's per kilogram dry air, but let's just call it H1. Okay, so I want to know, wouldn't it be nice if I know my H2? So if I know my H2, I will just make a line, hit with W2, and I will know where I will end. How can I get my H2? How can I get my H2? The first law, right? This, what is this guy? H air 2 plus omega 2, H vapor 2, what is that? What is this thing between brackets here? That is H2. That's the total H2. It's H air plus omega 2, H vapor 2. This is the total enthalpy, the mixture enthalpy per unit mass dry air, right? See, the M dot air is waiting. Okay, and that's H1, same thing. So what's the difference between the two of them? M dot 3, H3 per unit M dot air. Okay, so just like the mass flow rate, the continuity equation that said that W2 is W1 plus the extra that you add, same thing, H2 is H1 plus the extra that you add, extra energy wise. What is it? Plus M dot 3 H3 divided by M dot air. That is the extra. So I come here and I get my extra enthalpy and I draw a line like this. When W2 meet this line, that is where we are going. That is state 2. Okay, so that chart is very simple, huh? Why it's very simple? Because reading that H from two different table. What two different table? Air table and steam table, right? I need to read this H1 is H air 1 plus omega 1, H vapor 1. Like I need a table for this. I need a table for that. I need to multiply by omega. So I mean, from the chart, I can just read this number and I will don't have to worry about, are they scaled? Do they have the same zero, H vapor and H air, right? It's a piece of cake. And then we will just move to the new H and we are done. So dehumidification is done easy, basically, right? By those two equations. This for the energy and this for the mass flow rate, right? And it's always per unit m dot air because you normalize things with m dot dry air. Good. All right. Next part, the adiabatic mixing of two moist air. And we can do this after the break. So let's take a 15 minutes break and we'll start again. 15 minutes break. Right, I think we should start again. So people online, can you confirm you can hear me?
Yes.
Yes, good job. All right, so today you guys are submitting homework 3 and we're gonna have a quiz at the end, quiz 5, and next week is a project. And note that the project is like 5 homeworks, right? That's why it's important. So each homework is like 10 points, but the project is like 50. So make sure you submit on time, right? You don't want to lose 5 homeworks. And then the first midterm will be the week after that. So next week is not the midterm, the week after that. Okay. Yeah, because the reason I actually thought about this, and I know it's gonna be annoying, right? But because I wanted to have 25 homework and quizzes, so that each one of them is, 1%. So it's easy for you to get the value. If I have less, then the mess would be weird. Like, what is one homework? And I miss one homework, and it's how much is it? There's something useful about one homework, 1%, one quiz, 1%. But I will try to make it an easy homework, okay? So that it's not gonna take that much time. Okay, good. Can you post the exam so we can get a heads up for studying? Yes, I will post definitely the exam for last week, no, for last year, but I'm not gonna post the solution because I will post the solution, at the end. But I want you to really, so here is one bad thing that can happen when you read solutions. You don't really work your brain, you just are reading the steps, and the steps are not going to be hard to understand because the steps are all continuity and momentum and energy equation, basically. And the steps are probably very similar to the lecture notes. There is nothing new. And so reading the solution does not really teach you that much and give you the false impression that if I understand the solution, then I am ready. I understand the solution. There's difference between understanding the solution and coming up with the solution yourself. It's the difference between someone who can read books and someone who can write books. Completely 2 different skill sets, right? Having a book that you can read and enjoy, and you see how did the writer do this, is completely different from how can I come up with that book myself, right? Especially the starting point. When the students always say, I am lost, I don't know where to start, that is the part. That is the part that you need to be able to get it by yourself. So when you read the homework solution, you are not lost and you know where to start. You just like following. And of course, it's easy to follow. But how do I think about, let me apply the energy equation? Or how do I think this has to come with thinking about the energy, the mass balance on the water vapor? And that's the part that you can only get when you just have a problem, you don't know what to do with it, and you hit your head on the wall to figure it out. That is the part, that is the training. And so I'm gonna post the exam from last year just for you to check your time management skill, okay? But I'm not gonna post the solution until the end. So someone say, I use the solution to make sure I am doing the problem correctly. Yes, only at the end. But the temptation for a lot of people is when you it's a little bit hard, I don't get it, let me see the solution. And that's when you lost that experience of trying to figure out whether you can go this way yourself or not. So you are posting the solution when you said at the end, yeah, like maybe one night before it. No, just one night before the exam. Like maybe Sunday, I post it Sunday morning, the solution, but I can post the exam, today. So the problem is, the exam itself, I can post it today, but I will wait on the solution until then. Okay. The exam is 1 hour, 3 problem. 1 hour, 3 problem. Like, how long do we get to take the exam? We'll just start it at 7, we'll finish at 8. That's when we're gonna have the exam. Huh? Does the exam have to be in person or can we do it online? So there, you can do either online or in person. The only thing when you do it online is that you just need to have the camera on in your Zoom. And the camera need to be looking at you so that we make sure that you don't have your older brother solving it for you. How many problems should we expect? 3 problems, 1 hour? So, I mean, you're gonna see the exam last year, right? And hopefully the exam this year will be same caliber. The exam is open book, open note, yes, and open internet, except for check.com. And I would know. I mean, I put 15 people on the last year. Okay, so I would know if you copy it from check.com. So, but it's open book and open internet. You can really Google, like, solve a problem. As a matter of fact, I said that at the beginning of the year. Let me say it one more time quickly. It's okay to look at the solution. Huh? I'm not going to say check.com, but even check.com, when you are practicing, it's okay to read and understand. But what people do is that they just copy without understanding. And when things go this way, you are not learning, and you will make a mistake, and I will find out, he will find out. So, but when I'm like an actual engineer, can I see what other people, how other people made the product? Of course I can. It's okay to do that, right? But it's this, like, I have no idea what's going on, but he must know what he's doing. Let me, or she know what she's doing. Let me just do what they did. That is totally wrong. Counterproductive, counter-educational, unethical, immoral. List as many bad things as you want. Good. So let's continue with this. So let's do. So now we are, the third application in this chapter is mixing. Adiabatic mixing of 2 moist air streams. And adiabatic saying that there is no cooling or heating while he's putting the 2 guys together. Where did we see this before? When he put 2 streams and he come up with something at the end. Does anyone remember? Open feed water heater. Exactly the same equation, right? The only difficulty here is you are trying to have 2 m dots also. So in the open feed water heater, there was just like m dot, same liquid, same vapor, I mean, same material. M.1 plus M.2 equal M.3. Now we have 2 mass flow rates. Air mixing and water mass flow rate is also mixing, right? And then, of course, the energy balance, which will be exactly the same. So what do you want? You can see here, there are 3 things at the end that we want to calculate. 2 m dots, when he say W or omega 3, he's actually meaning m dot air multiplied by omega. So that's m dot water. So there is m dot air, m dot water, and the temperature. Those are the 3 guys. So we have 2 continuity and 1 energy equation. Right? Those are what we are after, those 3 guys. So continuity equation. I mean, it's really funny that, I took how many courses as bachelor, like as a master student? I took more than 8, maybe 12 courses in my master, and then my PhD, more courses. In all those courses, there was no more equation. That's it for you. It's continuity, momentum, and energy equation in all those courses, except that sometimes he do it at very high speed, and he call that compressible flow. Sometimes he make it at outer space when the gravity, like there's not that many molecules, and they call that a rarefied flow, where the flow is like very little. Sometimes they just like put water droplets in the air and they call this multi-phase flow. Sometimes they make the liquid also combustible and he can react, and they call that combustion course. And then if the flow is like moving very hard, like fluctuating, they call that course turbulent combustion. But in all those courses, now there is only those three equations: momentum, energy. We don't have anything else, basically. So I mean, when you are in doubt next exam, just write continuity, momentum, energy equation, and the solution will probably will show up. Just list them. So m dot air plus m dot air equal m dot air. Sure. M dot vapor plus m dot vapor equal m dot vapor. Yes. And then he replaced this by omega m dot air. Omega m dot air 1, omega m dot air 2. So now for the first time, we have 2 m dot air. And for this chapter, so unification, we always had the same m dot air right and left. Inlet and exit was the same m dot air. Now we have 2 different m dot air, but they leave at the end together. And so he, just rearrange them by dividing over m dot air 2, and this can become this. Look at this equation. This equation, what are we after? Omega 3. We want to find out what is the omega 3 because of that mixing. Right? What is omega 3 at the end of that mixing? So imagine if m dot air is 0, someone just, or like very, very close to 0, someone close the valve, m dot air is like, I don't know, 1% of m dot air 2. If m dot air 1 is 0, omega 3 should be omega 2. And the same thing here, if you shut down if you shut down m dot air 2, or you make it very close to 0, omega 3 should be omega 1, right? So when you look to this equation, let's see if it makes sense. If m dot air 2 is 0, 0 gets multiplied by this, right? And omega 3 would be almost omega 1. And the same thing, if you shut m dot air 1, you make it 0, this guy would be 0. You multiply this by 0, then omega 3 become omega 2. Right? So that equation makes sense. And it's basically saying that omega 3 will be equal toward the guy with the largest mass flow rate. If you have the large flow rate, you will bring omega 3 toward you. Right? And if they are 50, so this guy over this guy equal 1, what will happen to omega 3? Omega 3 minus omega 2 will be equal to omega 1 minus omega 3, which will mean that 2 omega 3 equal omega 1 plus omega 2. Or omega 3 will be equal omega 1 plus omega 2 divided by 2. It will be the mathematical average. Omega 3 will be the mathematical average, like half basically, of omega 1 plus omega 2. So it's kind of a weighted average, right? Remember this equation in a minute. You will go back to it. And to get the energy at the exit, he's doing the first law of thermodynamics. No Q, no W, because it's adiabatic mixing. I mean, you could add some Q. If you add some Q, this would be this equation. But he's mixing without heating or cooling. So then what will happen? Energy in, 2 guys are coming, equal energy out. Rearranging, you get this. This equation, why we are using this equation? Why we are doing the energy balance? What are we after? T3. We are after T3. We want to find out how hot the air, how humid the air is leaving, and how hot the air that's leaving. T3. Okay. So the unknown here is this guy. I mean, H total is function really of T3 and omega 3. So knowing this is like knowing T3. Okay. So this guy here and this guy here, it's the same guy, diagonal. And this equation, look to this. It's exactly like this equation, except for not omega, it's energy now. So we should expect the same trend. I mean, kill m dot air 1, make this guy 0, and what will happen? H3 become H2. Kill 2, make it 0, and 3 will be 1. So it's the same thing. It's mathematical average, weighted mathematical average by m dot. All right? So graphically, those two equations that's coming from continuity and coming from energy will be like this on the cyclomatic chart. See where W3 is sitting between W1 and W2? It will sit depending on that m dot over m dot. Okay? If you are 50-50, you will sitting in the middle. Not just in the y-axis, but also on the h-axis. Where you are you at 1? Sorry, 1, yeah, 1 is here. Are you at 1 or you are at 3? Depend on the ratio. Okay? But what's really important in this sketch is when you add 1 and 2 together in a mixing, the output will sit on the line connecting them. This is very important. Okay? So on the cyclomatic chart, when someone tell you I'm mixing this and I'm mixing this, you should know that 3 will be at place here. Along that line, 3 should sit there. Maybe we need one more information to tell us where is 3, but it's on that line between them. All right? Very good. So, okay. So here's an example. He's giving us state 1, temperature and omega, and m dot air, and state 2, temperature, omega, and m dot air, and he would like us to find out omega 3 and T3. So this is just like number for you to practice, But it's this equation that will calculate omega 3 for you, and I guess the other long equation, this equation where you put the m dot and m dot, and you'll be able to calculate the H3. Right? He's giving you H1 and H2. Okay. So, but actually, graphically, all you needed is to just find omega 3. So if this equation, which is m dot over m dot equal omega 3 minus omega, this equation calculates for you omega 3. All you have to do is just take the line like this and intersect with the line between them. You don't really need the energy equation for it, right? The energy equation is really implied by the fact that I'm going to be on the line connecting the two of them. Make sense? So one of them was good enough. Very good. Okay. So a very good application of this humidification process is the cooling tower, right? And so those cooling tower are those pictures, we see in power plant when they had this huge thing that basically have big cloud leaving. That big cloud that's leaving is because we evaporate the water in the cooling tower. So A reminder is that in a Rankine cycle, and the first exam will have Rankine cycle and also have the psychometric stuff that we have been doing. So in this Rankine cycle, it's 1 and 2 and 3 and 4. So for the water to go from 2 to 3, to go from HG all the way to HF, who's doing this? It is the cooling coil that is sitting here, right? So it's this guy, right, that is doing, he's getting hot. He's coming with Tn and he's leaving with T out. Tn and T out. Okay, and because he's colder than the steam gave him his Q dot L. Make sense? Okay, so now this water that is doing this Q dot L, where is it coming from and where it's leaving? It's going to a cooling tower, right? So it's going like this, being sprayed into a big cooling tower, and the water that get pulled out colder will come back again. So the water will come here at say 35 degrees C, get sprayed and basically pulled back say at 20 degrees C. Okay, so that the cycle continue again. Right? So that water will go like this and then go outside in the air, get cooled like this to be ready again. So the cooling tower is taking you here, and then the condenser is taking you here. And the water continue in that journey. So for that cooling tower to do his job, he will have to get m dot water in the air. So the air is coming here at T1 and omega 1, and the air is leaving here at T2 and omega 2. And this, the m dot water here is omega 2 minus omega 1 m dot air. Right? And for that water to leave from this big cloud on top of the cooling tower, there has to be what? Makeup water, m dot makeup. So all that water that you are throwing away need to be basically put again into the cooling water cycle, right? And the difference between those two W's on the psychometric chart between W1 and W2 is basically how you are cooling yourself from T water. We said what? The water is coming, the air is coming at T1 and he's leaving at T2. Okay, and hopefully the water also that is condensing on him or evaporating is also getting cold. So what we need to figure out is, what is the temperature of the water? Will this water will be able to get really cold to the air temperature or not? So let's see the equation that control the cooling tower. So sometimes they need fans, sometimes, especially those big, huge cooling tower, they don't need fans. Why? Why they don't need fans? Because of the kind of the chimney effect, you know? You know why chimneys are so tall? Why, like if you have a factory like this, usually it will have a really big chimney next to it. Why do they build them so high? Two reasons. One is because the concentration of the bad stuff, you want it to be hopefully higher than the houses, right? Those are the houses in the city. So you want the concentration to be really high, but also because that height will determine what? Can you guess? Why this height of the chimney is important? Which is important because, huh? I can't hear. You want the exhaust to be cold? No, not really.
Is it because of the higher velocity of wind?
So it's you need to go higher for the concentration to disperse. That's correct, but there is something else also, not just related to the wind. Buoyancy force. That chimney, can drive the flow by itself. Just like the example that I was showing you when the sun was heating the chimney. So the height, rho GH, is a delta P that you are creating. So the pressure, I mean, think of this, what's the pressure on top? The atmosphere, right? Pressure on top is the atmosphere. Isn't it the atmosphere minus I mean, shouldn't it be here the atmosphere, and then on the top it should be a little bit less than the atmosphere? I mean, that would be someone like, what is the pressure here? Let's say the atmosphere. Okay, what's my pressure in the second floor? What is it? The atmosphere minus one floor height times GH? Yes, theoretically speaking, it is, but you know what is, 6 meters or 7 meters between friends? 7 meters of air, that's nothing. You know why we have one atmosphere 10 to the power 5 on top of our head? Where this is coming from? Why I am standing, what is going on? Why I'm standing here with 10 to the power 5 Pascal on top of me? What is the height of our atmosphere? 10 kilometers. What is the pressure I'm carrying on top of my head? Rho GH. Okay. Rho air, how much? How much is rho air? Anyone? Someone put a gun in your head right now and said, what is rho air? Confess. Guess, take a guess. Huh? No, rho, density of the air. It has to be kilogram per meter cube. Rho is the density. 1.2, right? 1.2 kilogram per meter cube. Let's call it 1. And what is G? Can't hear. 9.81, right? The gravity, right? Gravitational acceleration, let's call it 10. And then the height of the air column on top of our head is 10 kilometers, right? So that is why we are carrying 1 bar or 100,000 kilopascal out of our head, just simply the weight. Of course, I'm simplifying the problem because the density of the ambient is not constant everywhere. As you go a little bit up, the density drop, right? and it's not exactly 10,000, and the gravity is not 9.8, but this is like the order of magnitude why we are carrying this much. So the chimney have hot air or cold air? Hot air. The density of that hot air is 1.2 kilogram per meter cube or less. Less. And so this delta rho GH will create a buoyancy force that will be equivalent to having a pump basically, or a blower pushing. Okay, because that air need to go up. Okay, so the taller it is, the more it will. And that's why if you look at natural flow or natural convection cooling tower, you will see that they are huge. They are huge natural convection cooling tower. We need a scale, I mean, like this. Look at that. So when it's really that big, you know, it can run without a single what? Without a single fan. He does not need fans to blow the air on him. He will just drive the air, the hot air by himself. Okay? But when they are short, they will have to have fans on the side. So if we just say cooling tower, you will see those guys. Okay, so those guys are really short, and usually they will have, you'll see the fans on top of them. Okay, or something like this. So that is a cooling tower. But it's because it's short, he can in here. That's a good sketch. You can see the fan driving the air through. All right, makes sense? Very tall one can drive by buoyancy, short one. So natural draft. And so it runs without electricity for the rest of his life. But guess what are we losing then? I mean, we have to pay upfront. We have to put a lot of money to build that massive concrete structure. And then it lives basically rent-free for the rest of its life. Right? The short one, you can just put them like this over 1 month. But then for the rest of the life, they just like keep sucking energy from you for their fans. Okay? Good. So a fan is over here. Water at T1 is being sprayed, and T2, the whole job is to make T2 less than T1. Otherwise, we have failed. Right? And the air is coming at T3 and omega 3 and leaving at T4 and omega 4. And of course, omega 4 has to be bigger than omega 3. Otherwise, how does he do his job? Right? If there was no omega 4 bigger than omega 3, then it's not an open cooling tower. It's just a radiator. It's just a box where it's like air cooling the water that's going into pipes without taking any water out. Right? And when he does this, if it's like dry cooling, then the best that this water can dream of is to get as cold as T3. If it's dry cooling, the best the water can dream of is to basically get as cold as T3. Right? Very good. So while he's being humidified, I guess, and his omega is increasing, he's cooling down the water. So now the question would be, well, how much is the m dot water that he's taking out, so that we can, you see the makeup water, that water need to replace the amount of water that is being swept off. So we need to figure out, well, how much we need to keep adding water to do this cooling. So we're gonna write what? Mass balance and energy balance. That's it. And so hopefully between those two equations, you'll be able to get m dot water and m dot. So mass balance, here is for the air, and here is for the water, vapor, right? And notice that this m dot and this m dot better be the same. Otherwise, the cooling cycle of the Rankine cycle will suffer, right? So if you think this water need to be equal to that water, that leave the makeup water to be exactly this. That's the makeup water. M dot 5 is m dot air and the difference in omega of the air. The air get this much humid, multiply by m dot air, and you get how much water is taking in. That's your makeup water to maintain the same m dot water in the cooling cycle. Make sense? So in order to find out how much is the makeup water, you just need omega 4 now. Because you know omega 3, that's the limit. We just need omega 4. We need another equation. Where we should go for the other equation? What else we have? We finished all our continuity. We did continuity for air, continuity for water. So what's remaining is maybe energy balance. That's what's left. Right? So by doing it, I guess that it's in the book, I didn't have it in the lecture note. By doing the energy balance, you find a really long equation that eventually will tie, and there's an example, really good example in the book, maybe you can look at it next time, something. But he basically tied the omega exit with the temperature and the temperature of the water and temperature of the air. Because when you think about it, m dot h n plus m dot h n water n and air n equal m dot water leaving and h water leaving. So if you specify, I want you to call me 5 degrees, for example, you will be able to, the only unknown in that equation will be how much is the energy out. Okay? And that will allow you to get the omega. Questions? Any questions online? Okay. Good. So a few slides about, so why we are using all those, why those psychrometric charts are, and psychrometric calculation is useful. So air handling units, AHU, are one of the really important applications for this. And you see in that building, he is having multi-store, and in each one of those spaces, there is just a place where he can send the cold air and receive the hot air. And those are brought into an air handling unit where you can get the hot air, hot and humid. Okay? And you have to return him as cold air again. Right? And you can have one air handling unit for the whole building, or you can divide it into different zones so that maybe the first 2 floors were like commercial and those are residential. They don't have the same operation, same capacity, so you can have different sizes of machines. Okay, but the point is, these are supposed to return back the air ready to get the load out. So if I told you that the optimum temperature for humans is like, say, 70 degrees Fahrenheit and 40% relative humidity, will that be, when you are designing this air handling unit, those optimum conditions, will they be the outlet that's going to the building or the inlet to the air handling unit? Which one of them should be the 70 degree and the 40% humidity? The optimum condition should be on the inlet to the building or the outlet from the building into our air handling unit. So basically what I'm saying is, you guys love to be at 70 degrees. Should I make the duct going into you at 70, Or should I make sure that the exit from this room is at 70? The exit at 70. So the inlet need to be actually colder, right? Colder and what? And less humid, yes. So if this is your optimal condition, I probably need to be somewhere here, right? So then when I go into your classroom, this would be one that is basically leaving, and maybe the two that's coming in should be here. Okay. And so then this go into our air handling unit, get processed, maybe mix it a little bit of stuff, but then the air come cold and ready for you. So he will go up like this. It's actually like two parts. Two parts, right? A part that get him more humid and a part that get him hot in the heating, like in the cooling application. So this is because we just need cooling, and this is because we just need drying, right? So this is the latent cooling, and this part is the sensible cooling. Okay, if we read on our enthalpy, and we can see the difference between those two H's. So maybe I should call this Q dot S and I should call this Q dot L. Latent cooling and sensible cooling. Make sense? Right? Latent cooling and sensible cooling. So what will determine whether this classroom will go like this, or will go like this, or go like this? You know what determines that slope? It's the ratio between this Q dot S and Q dot L. Okay, and what determined that? The application, the space. If this was a data center, bunch of processors like Pistol Beat, the cluster that we are using for our calculation is in Stillwater called Pistol Beat. We had an outage last week, lost the weekend, didn't get any calculation out of it. That bunch of CPU, like a lot of computers sitting in one big room, mainly is what? Q dot S or Q dot L? Sensible cooling or latent cooling? Does computer make water vapor or just make dry heat out? Dry heat, right? They are mainly just like dry heat, right? But if I am air conditioning a theater, a movie theater, those are a lot of people and they keep breathing CO2 and H2O, right? They will fog that place if we don't remove the water vapor out, right? So then it's the application that will determine the ratio between those two things, right? And what is the scale that we read here? That is kilojoule per kilogram dry air, right? So that delta H, I mean, we can call it delta HS and this delta HL. All it needs, this delta H, is to get multiplied by m dot air, right? So this Q dot S is simply m dot air, dry air, delta HS, right? And this Q dot L is the same thing, m dot air, delta HL. So we can figure out, I mean, if we have the target condition that we would like to keep the people as, and you know the ratio of Q dot L over Q dot S, you can draw what? You can draw a line and say, you know what? I think the inlet, this is the exit, huh? This is what will leave. I mean, let's call it 2H. And 2 is here. 1 should be along this line. How did I know that? Because the slope is exactly my slope. Actually, some psychometric chart will have on the side over here, we'll have a protractor so that you can get the Q dot L over Q dot S. So you find your exit, you draw the line parallel to this, and you will be able to say, I should be somewhere here. Anything along this line will get me, sending it to that space will work for us. Okay? So when you look at the chart, this one doesn't, but you can see, actually I apologize, our has to, but it's not as explicit like this. You know, it's not an actual angle. How did ours have? I don't see it. No, it's there. Why? Did you notice? This point? Okay, how is that having the ratio? I don't see it. How? What is that? That thing. Sensible heat ratio, Q dot S over Q dot total. Okay, how does this work exactly? What if my Q dot S is 30%? 30% is sensible, huh? And the rest of the Q total is all latent cooling. So what do? I come here, stand here, and draw a line from here, from this origin to 0.3. That would be the slope, right? Can we draw here? Draw line. And we do it like this. Okay. I mean, I assume I did do it. Yeah, wow, I did it great. Good job. So here from this is the slope of sensible heating 30%. Okay. So now if like you want the people to be sitting at, say, this location, this is their ideal position, then you tell yourself, I need to be parallel to that line. So I mean, assume parallel to this line is like something. Does this sound good to you? Like this, right? So if the inlet is here, that work. If the inlet is here, that work. If the inlet is here, that work. Any one of those guys, if you introduce it into that space, he will go up like this. Okay, got it? Yes. Right. So the question is, how did you, when you were designing the system from scratch, how did we decide that ratio? Okay, and also, here's another question. How do we determine that this is the optimum position? There are charts that tell you what is the comfort level for people at the gym, or people in a movie theater, or people in a classroom. They will tell you what's the optimum. People in winter, people in summer, people in a formal party. Okay. So you can, the target, there are tables for this. Okay, now the second question is, You said that we know the slope. We know the Q dot S over Q dot L or Q dot S over Q dot total. How do you get that ratio? Well, when you are designing the system, you basically you can design the system for a certain load. So you are saying, well, I have an off space, and that off space will have two BCs, and there will be two guys working here in that room. Okay. And there are actually has tables to tell you, I will show them to you next, that will tell you those equipment will generate this much QS and this much Q2, or like QS and QL. So you will have to do Q dot SI sigma I over Q dot SI plus Q dot LI. And you add those guys. So I didn't, when I was doing my senior design project, I didn't do it in HVAC, but I had a friend, I did it on crude oil pipeline design. But I had a friend that did their senior design on HVAC, like making a big system for a whole building. And they spend almost half the term, half the semester on coming up with the load calculation. Okay? Because it's not just looking at table, it's also where is the sun? A lot of the load comes from the sun. How many windows do we have? What time of the year the sun is, we are calculating this for, right? How much infiltration is going in? That load calculation is the life of the people working in that field. To be able to figure out that building would require this much Q dot S, this much Q dot L. And then they will design the system. Once you have those loads, then you move to the next step and you start designing the architecture of the machine itself. Okay, so to answer your question, how did we come up with those things? Load calculation based on tables and based on the building, the wall, nature of the wall, right? I mean, it's amazing how much time did they actually spend on that, just load calculation. Now, but something weird of what I said right now, I'm surprised no one asked about this. I just said right now, any point here will work. So what are you saying? Are you saying that we can send the air at 15 and it will work, at 10 degrees it will work? Are you kidding me? Like what? So that air coming from the duct into our room here can be at 15 or 10 and 5 and that still work for us? How is that gonna work exactly? I mean, yes, it will follow that path, but who said that it will end up here? What is the missing link here? Not the omega, no, it's the, no. So remember, we are sending 1 and we are pulling 2. This is 2 and we are saying where is 1. So what decide where should 1? I'm telling you, any one of those could be 1. It's the m dot air. So m dot air, H2 minus H1 is going to be the Q dot load. So what am I saying then? I am saying that if you don't want to send a lot of air, but you still want to carry that load, you better have smaller H1. So if you're just going to give us like this much air, give it to us at 5 degrees. But if you're going to send us a lot of air, you can get away by sending it a little bit hotter. Because of course, from the cooling coil point of view, he doesn't like to cool the air that cold. Problem with the COP, problem with insulating the ducts. But at the same time, saying, okay, then let's just cool 5 degrees so that our cooling coil will having a very good COP. The HVAC, the mechanical vapor compression will have great time sitting here. Just cooling 5 degrees, it's a piece of cake, right? The problem is m dot air will be so big, right? When I was a graduate student, one of my friends, he had the corner office. So all the graduate students were in the second floor, and the professor were in the third floor, and the classroom were in the first floor. Okay, labs were in the basement. It's funny that our labs were like in my first day, they told me all those lab doors, they are explosion proof, so that if anything went bad in the lab, even if explosion happened in the lab, that the building will be safe. And I was like, how does that make me feel safer? I'm gonna be on the other side. Like, are you kidding me? That's terrifying. That they're like, okay, let the student explode, it's fine. You'll be safe. It's just anyway. So that friend was his office was the corner office, okay? And we were so envious, like a graduate student with a corner office. But the first time I went to his office, I didn't envy him. Why? The whole exhaust duct, the air that will pull the air, was going into a big duct into his corner, the corner of the building. And man, you could hear the air moving in the duct. And I was telling him, his name was Sergey, he was Russian. And I told him, Sergey, how could you even sit in this office? Can't you hear? And he said, hearing what? Like, so he hear his ear after so much, time there, basically canceled the noise for him. He cannot really hear it anymore. But it was so, so loud. So that funny story is really trying to tell you that, no, you don't want a lot of M dot air, because that means either really big ducts, which you don't have ceiling for. Maybe here you have ceiling, but like in actual offices, you cannot have the full ceiling drop too much. Right? So the duct need to be smaller. You cannot allow them to be big. And if you say, but I'm going to speed up, I don't need a big duct, and just let them go super fast, well, you are going to make the people go deaf, or at least be irritated and say the HVAC engineer is horrible. Look what he did in this building. Right? So maybe a compromise between, how cold the air is, right? And also, one final thing thought about this is that in order to have the exit at 2, we send the flow coming in at low temperature. We don't want to hit those people with 5-degree air or 10-degree air. That's too cold for them. So that's why you always see what diffusers, right? Like in the inlet duct, it needs to be diffuser that send the air away from the people, send it in the room before it cool down to the people. So when I was assistant professor, I had a small office in the first floor. Before I got tenured and became associate professor, they gave me a bigger office on the second floor. My smaller office, that duct was on top of my head. And it was like, oh my God, I'm gonna get headache in that place. So I went and I basically put, you can buy those, by the way, you can buy like a plastic diffuser that you can, it look like this. So say if the air is coming so strongly in your child bed, for example, I have the same thing in my house with my kids too. So you buy this thing, right? And you attach like this, and then it's sent all the way away from the, say the child sleeping over here on the bed, right? The point is the air coming from the duct at 1 is not the good air. The exit from the room should be the good one, but the one coming from duct, that's too cold to have it in your skin. You need to diffuse, mix with the load, the sun, the heating from the sun, before you allow it to interact with the people in there. Okay, make sense? Right. So, I mean, let's take a 5 minutes break, and then we can go through the homework and the project. Okay, 5 minutes break.
Dr. Sloan,
Yes.
is there like a cool prop dot in like an actual MATLAB file, or is it just through Python?
See, that is a problem. If there was coolprop.m, it would be as simple as just running in file. But unfortunately, there is no, it's all like a shell, a MATLAB shell.
Yeah, that's exactly. So you got to download a Python interpreter. I did that. But it downloaded one that wasn't compatible.
Yes, I wonder if it's much easier since a lot of you guys know how to run Bison. You just run the whole thing from Bison. I mean, just like write a Bison code to simulate the.
I don't know.
How come you didn't take 30 what?
Making that next
You are okay because that's where they learn Bison.
semester. You don't learn.
3,400 like what's called this course? 3,000. 3413 computer method 3403, right? Who took computer method? 3403?
Yeah.
3403, right? So they learned Bison there. So anyway, so I mean, for this particular, we will go through the project in a minute, and I don't really need you to optimize it. If we needed to optimize the solution, I would have said you definitely need coolprop. But the way that because I realize how coolprop is annoying to install, the way the project read right now is run 3 different refrigerants at any property that you pick, any test condition you pick, and then in task 4, make it more accurate by adding superheat and. But then at no place I said find out the optimum design. So you don't have to have a cycle.
I know, but I don't know. I wanted it anyway, but now I thought not working as a whole on my machine now it's just all sorts of.
So any Mac has Bison underneath it, right? You know that,
Yes,
right? I mean, you just go to the shell and you run it, right? I mean, let me share my screen here. So here's my Mac machine. I just go to my shell like this. And then I tell him Bison 3. I'm in Bison already. And then I can write the code. Right? I can copy and paste, I guess. Hello. And you write hello, but of course it will be ideal if you like have like an editor, right? So I have this this editor over here, and then you can use it, write new codes, right? And you can run from it. It's free and it's very convenient. So any Mac can run a Bison code. So if we download coolprop and put it there, and all you need from coolprop is like give me the H, and you have like you will just have to learn very few things in Python. It's like how you can do a simple calculation. All you want to calculate is Q.L and Q.H and the work, which is M.delta H. So it's not that hard to teach yourself, you know, just like few lines in Python. But of course, ideally, also we would learn how to install coolprop, or someone of you will manage to figure out how to install coolprop easily under MATLAB, and then our problem will be over. Right? They actually have instruction for installing coolprop, but problem is it's machine specific, and if your machine does not exactly match what they are describing, and you are not really that great in installing things, you did get to work?
Yeah, in MATLAB, I started my version that told the version to use.
Okay,
Because I just type in fiber, just finding that first one in frameworks. But that's no longer there, but the framework's still there. That's why I can't use. So
Okay.
finding it, that I can find it. So
congratulations. Now, if you can share this with everyone, that would be helpful for some people. So just send an email to the class or something. All right. Think we should start. So people online, can you please confirm you can still hear me? Yes, good. All right. So let's go through the homework first, and then we will have time for the project. So let's start with number 2 because it's the easiest, right? Let's start with the easiest. So please find the mole fraction and the mass fraction. I guess. Yeah, that was the older version before you guys told me, well, the mole fraction should be X, should be Y, not X, so that we are like that checkbook. So I did change it and I uploaded this new version so that we are consistent with the book. So some books use mass fraction MF, for example. But anyway, so what is the mole fraction and the mass fraction? The mole fraction of the product is easy. It's 8 divided by the total, right? That is the mole fraction. And ouch, it will be this 8 divided by 8 plus 9 plus 47. What is the mass fraction of CO2? 8 times 44. What's 44? The molecular weight of CO2. 12 plus 32, 44. 8 times 44 plus 9 times 18, 18 molecular weight of H2O plus 47 times 20. So I did it for the 8 CO2. This is mole fraction, mass fraction. We also do it for the 9 H2O. It will be 9 divided by this, and 9 multiplied by 18 divided by this. And then the nitrogen. Piece of cake? Yes? Good job. Okay. Number 3, a little bit harder. So number 3, he said moist air was 20 degrees, and with bulb temperature of 10 degrees. So so what is the first 20 that he's talking about? It must be the dry bulb, right? It must be that the dry bulb is 20 and the wet bulb is 10. So I can come here at 20 degrees C, and I come here at 10 degrees C. That's the wet bulb, right? Wet bulb temperature. And this is the dry bulb. And so if I go like this on the constant H thing, then I will hit number, that's 1. That's the air. Make sense? Dry bulb, wet bulb. And I can read W1, I can read Phi1, right? Right? Yes. Okay. And so $20, and then enter a steam spray humidifier. He's throwing steam on him. Mass flow rate of the dry air, 100 kilogram per minute. That's m dot air. Saturated water vapor at 110 degree. Saturated water vapor. That's HF or HG? HF or HG? Saturated water vapor. I can't hear. G, yes, G, because it's gas, not HF. Right? On the TS diagram, F is the liquid, saturated liquid, G is saturated vapor. Okay. So we got the H we are throwing in. That's like in this example that we solved today was H3. He's injected the mixture. There is no heat transfer with the surrounding. Okay. So like just adiabatic humidification. Pressure is constant at one atmosphere, 101.325 kilopascal. Please find out the relative humidity of the incoming air. That's easy. That's just like reading from the chart. Where is phi1? Please find the required steam mass flow rate kilogram per hour to increase the relative humidity to 70%. Okay, and find out the dry bulb temperature. So he's saying you got yourself, You got yourself state 1 and you can read phi1. Now he want to go up to phi2 equals 70%. All right? And he want to figure out, in order to do this in that humidifier where he's throwing water, how much is m dot steam that need to do the job? Okay? You need to go, I mean, I don't know whether, he probably is not going to go like this because the steam is really hot. But he's going to go in one of those directions and he will end up here. And he's just wondering how much m dot steam can do that job. Okay, and once you find your point 2, they will tell us also what is T2. Okay, so what do you guys think? I think that's a kind of really energy equation, right? It's kind of energy equation, but you know what complicated thing is that he does not tell us what's W2. You know, if I know W2, that would be so easy. Why? Because m dot air multiplied by W2 minus W1 would be m dot steam. And then I get m dot steam from here, and then I go and tell myself, you know, I do the energy balance, and then I can find out the temperature at the exit, right? Continuity will give me the m dot steam, and the energy equation will give me the temperature at the exit. I mean, still it's the same problem, but it's written such that you just want phi2 equals 70%. That complicated things a little bit. Why? Because phi2, how is it related to W2? Well, phi2 is related to BV2, and BV2 is related to W2. Right? Remember the equation between omega and B vapor? What is that equation? Does anyone remember? Omega was what? 0.622 B vapor over B air minus B vapor, right? So, I mean, if I know W2, I'll be able to calculate B vapor 2. And how is B vapor 2 and phi2 as related? Well, BV2 over B gas 2 is phi2. So, I mean, this require what? To solve it. What does this require to solve? I wanted you to say require trial and error. It really requires you to assume, huh? It requires you to assume kind of W2. Then things will be easy. And then you calculate everything. And then you check, is it really W2 that I assumed or not? It requires some kind of iteration because the way things are, you know, like this need a steam table, you know, to get big S2, you need T2. Then you go to the steam table, get the B vapor 2. And because it's a little bit hard, right? And I'm such a nice person, nice professor. I am. What did I do? What is this? I think it is the MATLAB code you need. That is the solution. The only, I'm going to show you the full solution. The only few lines before it is, the input value, like it's kind of try and error. So this, let's look what's happening over here. He's using the schematic chart MATLAB file to do what? Knowing T1 and TW1, which is, we know T1 is 20 and the wet bulb temperature is 10. So you just, the line before this, you need to give him what's T1 and what's TW bulb. Okay. And of course, P1 is the 101C25. And what he's getting W1 and P1 and H1 at specific volume of 1. Those are the things that you are getting. And the thing that you are giving him are those that's missing. This is how you can use psychometric chart in case you want to use it for your project. The way to use the psychometric chart is you have to have this guy and run it. So in your MATLAB, you will have to have the psychometric chart new file. Okay? And let him run first. He's come. And once he's running, here, this guy, psychometric chart new, put it in where you keep your M file and just tell him to run. Add to the pass. Okay. Very good. And then after that, you would run here, CT1, T wet bulb 1, and B1. Okay. And B2 equal B1 and M dot here. Okay. Don't look at this now. Close your eye. Don't look. And then, so when I run this guy, what he will do, he will calculate W1 and P1 and H1 and V1. The three things that are missing are the three that I'm giving him. If I know, for example, P1 and W1, I would give him P1 and W1, and then I would ask him for the dry bulb temperature, for example. And wait, question. So the question is, so in psychometric chart, MATLAB file, this guy, those are the unknown or those are the unknown? Those are the known. This is what you give him, and this is what he's calculating for you. Yes, he's calculating them for you, whether you need them or not, but he will calculate them for you. Okay, so I know for sure I need P1. That's why I'm telling him calculate phi for me. Because the problem said what? Calculate the phi1. So he will calculate this. So when I run this guy, he will tell me that phi1 is 24%. Okay. Make sense? All right. So back again to the problem. So what's going on here? He's calculating W1, and then he's doing W2 equal W1 plus M dot steam over M dot air. What is that? That's the continuity equation I've been writing all over today, over and over. The amount of water you are spraying or the amount of water you are condensing. Whether you are spraying in or condensing from the air stream is simply M dot air, and then W1 is W. If you are humidifying, it's W2 minus W1. If you are dehumidifying, you are sucking water out of them because you are cooling them. It will be W1 minus W2. So this equation will calculate W2 if you know M dot steam. Make sense? And then he's using the steam table, X steam, to calculate that HG, right? HG at 110. That's how you call it from MATLAB, from XT. And then what is that? That is the first law. Huh? That's what I just wrote over here. When I said m dot air time delta H equal m dot steam, time H3. If you divide over m dot air, you divide over m dot air, what you will get? You will get this. So m dot air cancel, m dot air cancel, and this become W and W. M dot steam over m dot air, that was W minus W over m dot air. So that is the first law. And what you get from this, you get H2. So now I have H2 and W2. That is two things on, W2 and H2 are two things on, on the psychometric chart. If you know W2 and H2, that's all you need on the chart. Actually, like this. H2 will be like this, and W2 is like this, horizontal and the tilted thing. You put yourself on the two. So he's saying, look at this. This is another way to use the chart. Now he's giving it W and H, W and H value, and he's asking for the dry bulb, Phi2, and specific volume and the wet bulb. So what was the problem statement? He wants to know how much m dot steam to get you to 70%, right? So this problem is doing what? Knowing m dot steam, he calculates Phi2. So what should I do then? Assume m dot steam, calculate Phi2. Not 70%, 60. Let's make more steam, 65. Oh no, let me add more until you hit 70. Okay, so just using this, you keep doing try and error until you get the magic number. And the magic number is, I guess, 45 over 60 kilogram per minute. Okay. I mean, I'm dividing over 60 to make it kilogram per second. And that will get you Phi2 to be 70.5. That's good enough for me. And here's the temperature. And basically this value is what we need to hit 70%. Okay, yes.
Would pressure 2 be equal to pressure 1 because it's constant throughout?
It's constant throughout, and also because it's an open duct. So, I mean, imagine you are spraying in an open duct. Why would the pressure at the exit be different from the pressure at the inlet? Especially if it's a very short duct, there's no pressure drop into it. Right? Air drop in pressure when you have a really long pass and you have pressure drop because of friction. But like a very short duct, it will have the same pressure. With the water you're spraying. Yeah, but still it's steady state and they are very close to each other. The pressure will catch up and we'll make sure that they are equal. All right, but see what I really love about this problem is that it gives you this. I know it's a little bit hard, but I wrote the solution. I mean, all you guys need to think is, man, he's calculating things that we are given, and he is using things that we are supposed to calculate. And then when you look at this, like he's calculating y, and you think you know x. But we actually know, we know the y and we don't know the x. Then you tell yourself, maybe I should do it by assume check, assume check, assume check. Okay. So I understand that you wish the homework was super easy and it would be just give me I never saw that formula before, you know, like why you don't just give me the formula, I put the number. Yes, that's what you should expect in regular courses. Huh? where you are just given the formulas and you are just like, we are testing your knowledge of remembering, kind of. Or like, you remember where is the formula? You remember which one we should use? You remember that you should use steam table with steam and Ferrion table with Ferrion and air table with air table. But in this course, you are supposed to be trained to study system and problem you have never seen before. Because that's exactly what will happen in the senior design project next year. They will give you a system that, or a problem that no one knows the solution for, including the company that's giving us this project. The company will give us this project because they don't know the solution. They want, like Korean, for example, they have their filter pump or like their filtration system always get blocked all the time, and they want to be able to figure out when it will get blocked. They want you to be able to, and they don't know how, and they have only one pressure sensor. So you need to be able to train in thinking about new problems. And actually, here is one funny story, it will not take much. So when I was a master's student, I mean, there was this one guy, his name was Ram Van Leer, and he was like one of the pioneers of CD. I had a lot of his papers, okay? And then when I went to Michigan for my PhD, he was a professor in my department. He was not my supervisor, and he was teaching me the first course that in my first semester, compressible flow. It's a graduate course called compressible flow. I mean, I was over the moon. The guy is genius. He actually used to play the bell tower. We had a bell tower in the campus. And like it's not like with keyboard, it actually knobs. And there's a bunch of bells and you play by knocking at you have a CD for music, for playing the music on that big bell tower. Anyway, the guy was genius. And in one of his exams, he wrote the following at the beginning of the exam. He said, this exam is going to be different from any exam you have ever taken before, because for the first time in your life, you will have to actually think. And when I think about this statement, you know, why would someone who's a PhD student didn't have to think all his life? Is he kidding me? I must have thought a little bit, but what he's trying, the exam was a little bit different in the fact that it was not on the course. It was, but it's bringing the same methodology. Same concept of like conservation of mass and momentum, but instead conservation of car, like solve a traffic light problem, for example. And when the traffic light turn orange or red or green, like how quickly will the car start to move? So this is a very important concept, and it's not addressed well, and that's why they created that course. You know, 3 years ago, this is the first time this course, I think, is being taught. And the whole idea is how you can basically attack new problems. Not that you study mechanical engineering and then we tell you go and study now, figure out how does bugs either. No, it's the same system, but it just, you shouldn't be surprised of the problem, right? And just not to make you upset, remember all the homework and the quizzes are how much? 25%. So each homework is 1%. So the today homework is 1%. How many problems we have? 3 problems. Each one of them is 0.3. This problem is 0.3 and the solution was given to you. This problem is 0.3, and yes, I'll give you that this is a little bit weird because like, where did we have this explanation? One of you wrote like, I've never seen any like this in the slides. Yes, you have not, but did you see this in the slide before? A compressor compressing vapor? Did we see that before? Yes, where did we see a compressor compressing vapor before in the slides? Yeah, on the BH diagram that we plotted so many times, that would be the compressor, right? We have seen this. We calculated the power, m dot h2 minus h1. He was pulling say R134A, but will the analysis, will the equation be different if I am pulling water vapor? No. Same kind of dome, huh? Pulling vapor, same equation, right? So it's not totally weird. It's not totally weird. And did we see this before? A heat exchanger where liquid or like stuff are moving, hot stuff are moving out and cold stuff are coming in. Did we see this before? Where? But in this course, I'm not saying that you should remember your heat transfer course. Where did we see this? Where things were heating each other? The closed water feed water heater. Did we have a homework problem on it? Did we remember the equation? What's the equation? Q dot equal Q dot. And what is Q dot? M dot delta H equal M dot delta H? Was that something new? The elements are there. Did we see this place before? Where two guys come and one guy leave. Open feed water heater, right? Liquid become vapor. Liquid is being sprayed and it becomes vapor. Isn't this the boiler? I mean, you are heating it with this guy, but it doesn't matter what is in the pipe, whether it's hot vapor or hot gases, right? So my point is, it's not totally out of your jurisdiction. It's part of what you studied, but the arrangement is new. And yes, it's scary when like, I've never attacked this before. I've never solved this exact problem, but that's what you should expect in a senior design project. There will be a system that you haven't seen, but the elements, if we did enough a good job in the rest of the courses, whatever that system, whether it's a UV launcher or whether it is a filtration system for an aquarium, or whether it is whatever the system you're going to design, you should have seen those elements in different courses. Okay, and what if no, it's too hard, I cannot do it? Then that's okay. The whole problem is 0.3 of your course grade, 0.3%. And if you do it totally wrong, every single line is wrong, Bemin will give you, when he's grading this homework, how much he will give you? 2, 2, 2. So you are not going to lose the 0.3, you're going to only lose 0.15. Okay? So 0.15. So I can, for the sake of making you like really go through this mental training and challenge yourself, you could lose 0.15 in 10 homeworks. Like for 10, I have license to give you 10 homeworks that each one of those homework have one weird problem. Not totally weird, but it's okay. You can lose 1.5% because at the end of the year, I'm going to give you 2% gift. So if you are 2% away from your A, you're going to get your 2%. So that 2% is my license to say, I can make the problem a little bit weird. That's okay, right? They are not going to, so I'm yes, I would love you to get that challenge, but I don't want anyone to get a B to learn. I want you to get an A and learn. And so there is 2% built in. That's on top of waiving the lowest 2 homework and 2 quizzes too, right? So enjoy that challenge and don't get scared or upset, or, you know, it's not a big deal if the homework is, I would say it's a big deal if the homework is so easy, the opposite. If the homework is so easy, you wasted your time, could have spent this time with your job or with your significant other or with your kids. Like, why did you spend 1 hour just like H1 equal, H2 equal, okay, where is the formula, Q dot? That's total waste of time, right? You don't do the homework, it's so easy. This would sound like bragging, but I'm not really bragging. When I was in middle school, the teacher, the math teacher would assign the homework for the math for everyone, and she would waive it from me. She say, everyone, this is your homework. And she would point to me and she say, you don't do the homework. You don't need it. You already done. So her point was like, why would I waste his time solving a problem that I know that he know how to do it. Okay, so if I give you homework just to waste your time, that's not really a good strategy. The problem needs to be a little bit challenging, a little bit, right? So hopefully no hard feeling, okay? So now let's see how we can do this. What he wants, label and plot on a TS diagram. Right? We need to label and plot on a TS diagram, and then we need to write the equation to model that system. Imagine if this was our project, and we would like to model this so that we can solve it and figure out, for example, how much he's doing. So first of all, what is he doing? He is desalinating water. He's telling us over here, seawater at that rate, m dot water plus m dot salt, enter at room temperature. It's heated in the exchanger before it is sprayed, heated over here. Why is he heating it? Why the incoming water is being heated? Why? Does anyone figure why he's heating the water coming in? Huh?
Less work for the compressor.
Because he want to harvest. It's less work for the compressor, yes, but he's also want the hot water leaving and the hot brine leaving, not to steal our joules and go away. You want to let them go out broke, right? You want to get their joules before they leave. Because I mean, who's paying for this? It's the compressor. When you put a big control volume, you will see what's going on. Work coming in, hot guys leaving. No, you're not leaving as hot guys. You're gonna leave us broke the way you came to us. You came at 25 degrees C, you're gonna leave at 25 degrees C. Ideally speaking, right? Okay, so he heat them. He hit the brine, sorry, the fresh water with the exit guys, and he's saying that now this m dot water, not all the m dot water evaporates and go to the vapor. Only how much R m dot water, where R is called the recovery ratio. So if 50% of the water become vapor, and of course what happened to it has become vapor, get compressed, get condensed, and leave, you will separate 50% of the water into clean water. That's called the recovery ratio. So imagine if you do 100% recovery ratio, what will be left over here?
Nothing.
Salt crystal, right? That is the ZLD system, zero liquid discharge, right? And I send you guys to video explaining exactly the cycle. Have you seen it? Did anyone see it? Where did we put it? Did I? Yeah, video 1 and video. There's video 1 and video 2, right?
Mechanical vapor compression
So
reduces the energy.
So the compressor, or the vacuum pump, also known as vacuum pump, also known as vapor compressor, he take that hot vapor and he condense that hot vapor into liquid while doing what? While the water that come from the top get turned into vapor. So he's recovering the latent heat. The hot vapor become liquid while the water that's being sprayed, not sprayed here, it's being sent into a film, is basically being turned into liquid, right? So that is how this thing works. Vapor, hot vapor is turning that liquid into vapor while he himself condenses. All right? So Okay, so now I understand the different components. So he wants us to put numbers on it, on things. So why do we put number? We put number when things change from one to the other. Like you compress things, for example, then you would call it, I need different color. We call it 2. Okay, so this is 1 and this is 2. And then after he goes through the cooling, the steam get cooled by the water boiling on him. Then he becomes 3. And then he goes through a condenser and then he becomes 4. Right? And then this water coming in fresh, 5, get heated, become 6. This is still 6. Then it get mixed with something. This something, let's call it 7. And 6 and 7 together become 8. And 8 gets sprayed and get heated. Right? And it gets heated into 2 things. One that is going to the vapor, and let's call this, say, 7. Now, what is weird is like, why this is 7 and this is also 7? There's a pond between them. Why did I do this? And the secret is, and of course, this is also 7. And then 7, say, become 9 after the heat exchanger. So why did we call it 7 and 7 before and after the pump? Say that again. But the pump, what does the pump do? Huh?
Overcomes
Pump.
gravity.
The pump is what?
Overcomes the gravity.
The pump is very little, right? It's just circulating pump. It's not an actual pumping pump. You know, it's not like the boiler feed water pump, which take the steam or the water from condenser pressure at 0.07 bar and take you to 220 bar, right? This is just a circulating pump. So yes, if you want to be super accurate, I mean, you can make it 7 and 7.1 or something, you know, like just a little bit change in the pressure, but it's not going to be a big deal. Okay. Is the one between 4 and 5. That's 9. Why did it change? Because it went through a heat exchanger. It get cool, right? So the reason why so some people said, just write the solution for us and let us read. I will do this because you need this before the exams. Not that this would be repeated, but it would be nice to see the solution. But what I'm really trying to do over here is I want you to think, or actually I want to see how I'm thinking of solving the problem. So rather than just like reading my solution, which again will be very simple because there is nothing really complicated. It's what I'm trying to impart on over here is, why do I think this solution? How did I think that solution? Okay. Good. So the compressor equation, m dot compressor would be m dot, well, we have seen it before.
H2 minus H1.
Very good. H2 minus H1. All right. And maybe maybe actually we need to see what happened in the evaporator to write the evaporator equation. But we can write easy things first now. The heat exchanger. How do I write the heat exchanger equation? There is 3 streams going on over here, right? So how do I write the equation for that heat exchanger? The guy that's being heated equal to the 2 guys that's being cooled, right? So maybe m dot, the guy that's being heated is new water, right? Which is m dot water plus m dot salt multiplied by H6 minus H5. That's how much they will absorb. That's equal to the other 2 guys that are being cooled. How much is that? m dot water R, that's the how much you recovered, multiplied by H.
4 minus 3.
4 minus 3 or 3 minus 4?
4 minus 3.
3 minus 4. Okay, why 3 minus 4? Because we are writing it such that this is how much did you get heated and this is how much you get lost. If you want to write it like the first law of thermodynamics, which what I always like to do actually, it would be sigma m dot out h out minus sigma m dot n h n equals 0. And you just write even blindfolded. You don't really need to see who is who. You just like, here's all the outlets, minus all the inlets. Okay, and that will work too. But here you are basically just like trying to invoke your physics of understanding. Here is one guy that's being heated, and here is the other two guys that's being cooled. So this is m dot water 1 minus R plus m dot salt. That is the prime that's leaving, and it's multiplied by
7 minus 9.
7 minus 9. Excellent. And we finished the heat exchanger equation. Yes. That is excellent question. The question is, so is the m dot salt coming in here? When you said it's m dot water plus m dot salt, is that m dot salt the same as the one leaving at 9? And at steady state, it is. The salt coming in is the same as the salt leaving. It is a very safe assumption for all engineering design to always assume steady state. I mean, if there is difference between them, then it will be the m dot salt building up inside the heat exchanger. And you will build up until you say, time to clean up, guys. Okay, so very good. What else is we can write? The mixer. When 6 and 7 come together and become 8. And for that, you need to tell yourself, I know this m dot. That's the incoming. And I know what's leaving at 9, but what is being circulated exactly in this branch, guys? How much is going here? How much is that mass flow rate? I mean, we know this is R m dot, right? And we know at 6 that is m dot water plus m dot salt, right? And we know what is leaving over here. It's 1 minus R. But how much is being circulated upward back again? Why is he circulating it? I mean, that system can run without that branch going up, right? It could run without that branch. You just spray the water, some evaporate, go to the evaporator, go to the compressor, that's your distilled water, and the rest that didn't, will fall down. Bye, guys, leave. Why is he circulating?
So you don't
That's how
have
you
as
think
many, so you don't need as many systems because it can recirculate and go through the system one more time.
Yes, it's exactly right. Who's talking, guys? That's Robert, right?
Yeah.
So Robert is saying you can reduce the amount of system. He's probably thinking you need to reduce the, I mean, he does not think there's enough evaporation in one room. You think maybe we need more rooms. So it's basically the time the droplets stay in the air that will determine how much they evaporate. And so if they don't spend enough time, if they go and leave quickly, m dot vapor, the one that's leaving up at 1, will not be much. So by circulating, you actually improve the residence time. You also maybe keep the heat in the chamber so that the heat exchanger downstairs doesn't have to work as much to absorb the heat, right? So that amount that's circulated, that's really a design thing. And depending on how much you recirculate, if you circulate a lot, 7 and 8 will become almost the same temperature, become the same H. everything will be almost recirculating. Like the new fresh water coming in will be very little, and everything will just like circulate forever. And if you circulate very little, it almost becomes 6. All the water coming in will be almost 6. So what I'm saying is that we will have to model something like this. You will have to say, you know what, there'll be a design parameter here, let's call it X. And that will be X, or like, let's call it M dot X, for example, where M dot X is a ratio of M dot water. Just like cover ratio is a ratio of M dot water, you would say, I'm gonna recirculate twice the M dot water, or 7 times the M dot water, or, okay? And so now, once you have this M dot, now this elbow become a piece of cake for writing his equation, right? What would be the equation then? An open feed water heater equation. 2 guys coming in, M dot 6 multiplied by, not M dot 6, let's write M dot water plus M dot salt multiplied by H6 plus M dot X multiplied by H7 equal what? Help.
1 minus R, or no. Be M dot W plus salt plus X.
Yes. Multiply by
H8.
yes. Okay. We wrote the elbow, we wrote the heat exchanger, we wrote the compressor. So the only thing that's complicated is the evaporator. And for that, we need to look at the TS diagram for this. And so here is the TS diagram. So 1 get compressed up, asymptotically become 2. Maybe we should plot it here so that you can see. So 1 get compressed to 2. 2 is now superheated vapor. What happened to 2? It needs to become liquid so that we can drink it. So what do? We cool it. We cool it at constant pressure, right? Any cooling that does not get you to 3 is not good enough, right? It's not liquid. So 3 has to be like this. And then 3 get cooled in the heat exchanger to 4 at constant pressure, right? So now this 1 that's over here, where did it come from? It came from 7, right? Actually, it came from 8. So 8 is being sprayed and it's being heated to become 7 and 1. 7 is the liquid that will fall down, and 1 is the vapor that will go up. And where did 8 come from? 8 came from the mixing of 6 and 7. So 6 must be here, lower than 8. And 8 must be lower than 7 because it gets heated to become 7. Right? And where did 6 come from? 6 came from 5. Make sense? So 5 became 6, and 6 mixed with 7 to become 8, and 8 get heated to become 7 and 1. 1 get heated to become 2, then cool to 3, and get cool to 4. Now, what happened to 7? 7 get cooled in the heat exchanger to become 9. 9 could be, anywhere. 3 depend on how much cooling happened to it, but 9 could be like this. I mean, ideally, you would like to bring 9 all the way down, right? Just like you would like to bring 4 also all the way down. So 4 and 9 should go down, but they cannot get any colder than 5. So now to write the final equation which is evaporator equation, what is going on in that evaporator? This guy is cooling himself by heating 2 go to 3 by heating what? By heating 8,
5.
right? So I could just look to that that evaporator and tell myself there is inlet and outlet. I'm going to write the first law of thermodynamics. I'm going to say m dot n h n equal m dot h out, or I could basically just say I know that m dot R m dot water, that's how much vapor is condensing. And he condensed from H2, H3. That's how much heat he's losing in that chamber. And as a result of his cooling like this, he is taking my m dot water plus m dot salt plus m dot x, right? That are coming at H8. And he is taking them to H7 and H1. So actually for this, let's just take 2 parts. Let's say that the part that's 1 is m dot R, m dot water, and this get multiplied by H1 minus H8. And the other part, which what will fall down, that is m dot steam plus 1 minus R, m dot water. This guys got heated from H7 minus H8. Okay, so if this is complicated, then you can just say, I'm just gonna write a control volume. I'm just gonna write a control volume, ouch. I'm just writing a control volume like this and look at what is coming and what's leaving. Okay. And I see here 8, I see 1, I see 2, I see 3, I see 7. And each one of them has his m dot and his h. And so I'm going to just say sigma m dot h equal sigma m dot h out and in. Every h out get multiplied by its m dot. And the m dot could be easy, like 1. What is 1? R m dot water. And the same thing here, R m dot water. R m dot water. And sometimes it's hard, like this H8 m dot R, sorry, m dot R. This is m dot water plus m dot S plus m dot X. And what's leaving here? M dot water, m dot, sorry, 1 minus R, m dot water, m dot X plus m dot X. Okay, when you write those guys together, you will find exactly this equation. I guess we didn't write the m dot X, it should be here. Right? M dot X need to be inserted here. So I'm going to clean this up and post it for you, but this is a little bit hard. It's a little bit stretched from what we had before, but it is the same principle. Right? And what happens if you don't get it exactly right? You lose 0.15% or less. I mean, hopefully you wrote the compressor right. I mean, hopefully Bimin is not going to give you 2, 2, 2. It's going to give you, actually 4, right? 4 and maybe 3 and 2. So very little is lost. We don't have time for the project, but actually I think I want to just say a few things about it. Okay, so and the quiz, by the way, is very easy. So the quiz will take you 1 minute, really. So I mean, I think we can afford to spend some time in the project. So the project is basically saying that you are designing only the refrigeration cycle, right? So this refrigeration cycle has a compressor, right? That's sending things to the heat exchanger here, the condenser, and then throttling it to the evaporator. Okay, so that evaporator job is to cool the seawater, right? Because he said in the problem statement that there is a specific temperature that he wants to heat the water at, right? Those are 15 and 65, if I'm not mistaken. Is that correct? 15 and 65. Here. 15 and 60, right? So this air need to be cooled to 15, and this need to be cooled to 60. So what that tell you about this temperature? Is it 60 or higher? Higher. And if this air is 15, what that tell you about this water temperature? Huh? I can't hear. So the air in this room, in this humidifier, need to be cooled down to 15 degrees. So the temperature of the water that will cool the air to 15 degrees, should it be 15 or lower or higher? Lower, like what? No, let's make it 10. So this water need to be 10. So then what is the temperature of the refrigerant? If you want the water to be cooled to 10, then that refrigerant need to be 5. So let's make this 5, and let's make this, I mean, if this air is going to be heated to 60, this temperature maybe need to be 65, then maybe this need to be 70. So then effectively, just from this problem, you are basically telling yourself, I need my refrigerant pH diagram, I need this to be corresponding to 70 degrees and this corresponding to, say, 5 degrees. So now, depending on what refrigerant you guys are going to pick, that will correspond to different pressure. The pressure here, that will get you 70 and 5 is different if it's ammonia or CO2 or, right? You need to pick 3 refrigerants that will do this for you. And you would read H1, H2, H3, H4. You got your H's, then you got your W dot compressor. M dot refrigerant, H2 minus H1. Okay. Now, yeah, you do that for 3 of them, right? And for each one of them, you calculate the H's, you calculate the work. Now, to be able to calculate the COP, it's always the output over the input. Right? So what is the output that we're going to get from this thing? I mean, we need to modify, we come up with new way to measure how successful this refrigerant is. So how successful this refrigerant is will translate into what? M dot water that's condensed, which is M dot air multiplied by omega minus omega. Right? This is what you need to calculate the COP based on. How much does this cycle manage to get water for us? That is the correct coefficient performance for this place. Okay, so we benefit from cooling and heating, right? But how does this translate into MDOT? Right, so it's 8:04. I think let's do the quiz. So what does the quiz? You can get the quiz from the assignment. And I'm gonna pull it over here too. It's very, very easy. And it says here, so first 20% for saying whether you are online. And if you are in class, just write the seat number. And then it say for number two, bar two, for air at 30°. And 40% of humidity. Find the wet bulb temperature and the dew point temperature. You're gonna report two temperatures. Okay, you can use the chart, you can use the equation, whatever you're comfortable with. Write your answer, and you are done. Please don't forget to write the pledge. You say, I didn't copy, and help other students to copy in this quiz.
If we're using MATLAB, do you want us to post a screenshot of it or something?
Yeah, that would be super nice of you. Yes.
All right.
But you don't have to use MATLAB. You can just read from the chart, right?
So if we get our answer just from the chart, can we write down just what our answer is?
Yeah. You just say by inspection. Say by inspection, Here's my T wet bulb temperature, and here's my T dry dew point temperature.
Okay.
So by inspection, make the T understand that you just looked at the chart and you read the numbers. So someone said, I cannot find the metric chart. Where is it? It's the same file that's uploaded on Canvas. One part, the first page is SI, the second is metric. I said that earlier today. The second page is SI, yes. Right. Take care, guys. Good luck in the project.